Hey kiddos, today we're doing improper integration. This is different from integrating a rational that's improper, where your top is bigger than the bottom. You'll be able to tell. Improper integrals can look different ways, but the kind we're going to do today look like this. So we're going to integrate 2e to the x starting at negative infinity and stopping at 3. And there it is. That makes it improper. So if you have bounds that are infinities, it's called an improper integral. So if you notice on your flow chart at the bottom, I don't have, there's no flow that takes you to improper integrals. You just have to be on the lookout for them. So if you have bounds that are infinities, you're dealing with an improper integral. Now, the way you take the integral could be u sub or by parts or complete the square or any of the other things. It's just the bounds that make it improper. All right, but this one's going to be not bad. Here's how you handle improper. You cannot treat infinity like a number. So you cannot take this integral and then plug in 3 and plug in negative infinity. We have to sneak up on negative infinity. I'm going to use t. And now our integral becomes, I'm going to pull the 2 outside as well while I'm at it. E to the x from t to 3. And now everything is exactly what you already know how to do. So you got to work inside out. The notation is gonna destroy some of you because you're terrible at notation. But now we have the limit as t approaches negative infinity of, I'm going to go ahead and take the integral. The integral of e to the x is e to the x, and there's a 2, from t to 3. So the integral's done. First you integrate, and now we're going to evaluate. So I'm going to plug in my bounds, just like I know how to do. So I have the limit as t goes to negative infinity of 2e cubed minus 2e to the t. So I integrate, I evaluate, and now I'm going to take the limit. So 2e cubed is fine. It's great. I'm sure it's wonderful. This is the thing that is actually being affected by this limit. So let's pay attention down here. So this is going to be 2e to the negative infinity. Notice that I'm pulling this out. Like this is the one thing you're not allowed to do. You're not allowed to just plug in infinity. So 2e to a very, very negative infinity. Well, negative exponents reciprocate. So I also don't even really care about the 2 that much. Let's just focus on this thing. So the negative exponent reciprocates it down. So as the bottom gets bigger, this whole thing is going to 0. So this whole chunk is going to 0. Our answer is 2e cubed. And the word we use is that it converges. This integral converges to this value of 2e cubed. It approaches that value. So think about what you did just for a split second. Think about it. Use your thinking. You just told me that the area under this curve, starting at negative forever ago and stopping at 3, gives you the value 2e cubed. That should kind of hurt your brain. Like if I'm supposed to be accumulating area and I start at negative forever, how do I get a value? So your brain should hurt a little. Let's do one more. This time, let's integrate from 4 to infinity, 3e to the negative 3x. I don't know why these are all e's, but they are today. Okay, here's the piece that's making it improper. So we're going to sneak up on it. We're going to have a limit. I don't know why I always use t. I must have been taught that way, and now I can't do anything else. Let me pull the 3. E to the negative 3x dx. Now, this integral is not as straightforward. It's a u sub. I'm going to write it out because I sense that you're still kind of uncomfortable doing these u subs in your head, but if you can do it in your head, that's fine. So what we're turning this into, I'm just going to pull it down here to take the integral, and then I'll put it back up into my limit. We're going to have a negative 1/3, an integral of e to the u. So this is just very quickly negative 1/3 e to the negative 3x. So if you can do that in your head, I encourage you to. All you've done is undo this chain rule. You had a negative 3x that you had to undo its derivative of. So now we've got limit, haven't done that part yet, have to keep writing it. I still have this 3, don't lose that one. Multiplied by negative 1/3 just makes it negative e to the negative 3x. And this is going to get evaluated from 4 to t. Okay, top minus bottom, t to infinity. The top is negative 3t when I plug in. Minus a negative makes it plus e to the negative 12. And now when I plug in infinity, actually going to end up with the same kind of situation here. So this is going to end up being negative e to the negative 3 times infinity. I don't care about the 3. It's negative infinity. It still reciprocates. So 1 over big is small. This is going to 0 again. And this answer is e to the negative 12. Converges. Okay, let's talk about what it would look like if it does not converge. So those of you who participated in some of the phase 2 stuff last spring with Dr. Pickle, perhaps you remember doing some series and you talked about series converging or diverging. Converging means you approach a value. Diverging means you shoot off to infinity or you don't approach a value. So if I had a question and I took my improper integral and I did my limits and I did such a great job and I get that my limit approached infinity, either infinity, then I would say it diverges because it doesn't approach a value. Infinity is not a value. It's not a number. So that's what those would look like. I want to show you what your deltas look like because I gave you some that you're going to do just like I did in OneNote just now. Algebraically, you're going to do. But some of them I gave you graphical because I want you to see it. So here you go. You've got f of x as this function graphed here. We're going to use the slider to see accumulation of area and find each integral rounded to the nearest thousandth. That's 3 decimal places. So if I move the slider, you can see the area down below accumulating. And you can see your value here. Oh, good. Makes sense that it's negative because it's below the curve or below the axis. This slider takes me all the way to 20 and then it stops. So first thing down here, they want me to go from 1 to 5 and then 1 to 10 and then 1 to 15. That is literally taking the slider and trying to put it on 5 and then rounding to 3 decimal places, putting it on 10, rounding to 3 decimal places, and then 15. But then this bottom one is for this slider. So this slider starts you at 20 and then takes you much bigger, much faster. Like look at that top bound up at 15,000. So the question is, if we continue out towards, not to infinity, but towards infinity, do we ever approach a value? For this one, I would say we don't because it never settles down. Check out that answer. It's negative 2,300 and then negative 3,000. It never approaches a value. It does not converge. So we say this limit does not exist, and that means that this diverges. If it converged, it would start to slow down. It would start to even itself out, and it would approach a value you'd see. All right, give those a shot. Let me know if you need anything.